Welcome to acceleration. A background video for this one would be speed and velocity. However, if you don't watch those, you should have no problem. This is a self-contained unit. That video just provides a little more background. At the beginning, acceleration is a change in velocity with time. Acceleration is a vector, and acceleration has magnitude and direction because it is a vector. And you all know that because that's the definition of a vector. And the equation for acceleration is the acceleration vector is equal to the change in the velocity vector divided by time. Now, we're dealing with change in the quantity. You know it's a second quantity minus the first divided by whatever you're dealing with. So we have the second velocity vector minus the first velocity vector divided by time. And acceleration has the units of displacement per time squared. And examples of the units you will run into are meters per second squared and feet per second squared. As with velocity and speed, you may run into other units which are equally valid, but these are the two most common that you will run into and use. Now, a change in direction is an acceleration because both acceleration and velocity are vectors, and hence any change in the velocity is an acceleration. When you're dealing with things that move in straight lines, this really doesn't make any difference because the direction doesn't normally change because you're moving in a straight line. When you're moving around a curve or in a circle, this comes into play. Even though you are making an orbit in the same amount of time, you are still accelerating because you're changing direction. We'll cover more of that in circular motion. Here's our first example. A car accelerates from 2 meters per second to 12 meters per second in 5 seconds. We need to find its acceleration. Start with the definition. Acceleration is equal to the change in velocity with time, or v2 minus v1 divided by t. Notice I dropped the vector symbol over both acceleration and velocity because in this case we're not given a direction, so we really don't have a direction to use in a problem. We can't really call it a vector. We're dealing with the magnitudes of the vector in this case. Plugging the numbers in, I get the acceleration is 12 meters per second minus 2 meters per second divided by 5 seconds. Doing a little bit of arithmetic gives me 10 meters per second divided by 5 seconds. And we get a final answer of 2 meters per second. Notice that meters per second divided by a second gives us the per second squared in the acceleration. Next, we're going to look at the final velocity, or v2, that we can find using the acceleration definition. So starting with the acceleration equation, we can do a little bit of algebra and arrange it to get v2 is equal to v1 plus at. Now sometimes you will see this written as vf equals vi plus at, where vf is the final velocity and v0 or vi is the initial velocity. It's not uncommon in physics and other sciences or anything that uses math to see sometimes different symbols, but if you see them, don't be shocked. Example, a snowboarder is going downhill at 1.5 meters per second. If he accelerates at 0.5 meters per second squared, find your velocity after 4 seconds. And obviously we're going to use the v2 equals v1 plus at. We start with the equation, plug our numbers in, as you can see there. v2 is equal to 1.5 plus 2 meters per second. And we end up with a final velocity after 4 seconds of 3.5 meters per second. Welcome to first practice problem. A driver brakes and slows the car from 18 to 2 meters per second in 4.5 seconds. Find the acceleration. A little bit of a hint, so far the accelerations have been positive because the objects have been speeding up. Here the object is slowing down, so you can expect the acceleration to be negative. Work the problem. compare your answers to what comes up on the screen here. So go ahead and stop the video, work the problem. Okay, hopefully you've worked the problem and just didn't go ahead and take a look at what's up. Plug the numbers in, then get an acceleration of minus 3.6 meters per second square, which makes sense because the object is slowing. And we'd expect a negative acceleration because the velocity is getting smaller. The negative sign shows the car is slowing down, and a negative acceleration is called deceleration. Something you probably already knew, common sense type of thing. Practice problem number 2. How long does it take to slow to a stop from 35 meters per second if the acceleration is minus 3.0 meters per second squared? A little bit different. You have to find time instead of an acceleration, but to start with the basic equation, should be no problem. Stop the video, work the problem, and compare your answer to what's given. There you go. Now, hopefully you've worked the problem and just not skipped ahead to look at the answer. Write down the definition of acceleration, plug the numbers in, rearrange it, solve for t, bring it to the left side. You end up with 35 meters over 3 meters per second, giving you 11.7 seconds. Notice that this negative sign and this negative sign reduce, so you end up with a positive time. Practice problem number 3. A box sliding across the floor, decelerating at 0.5 meters per second square, takes 5 seconds to slow to 1.25 meters per second. What is its initial velocity? Little heads up here. You're told the box is decelerating, so you know that the value of the acceleration must be negative. Go ahead and use either the definition of acceleration or v2 equals v1 plus at, however you want to do it. Suggestion again, as always, stop the video, work the problem, compare your answer to what's on the screen. Here you go, v2 equals v1 plus at. As you can see, you plug the numbers in, grind them out, and you get 3.75 meters per second. I know I did 3 practice problems, much more than usual, but because of the number of times you're going to use acceleration in the upcoming parts of mechanics, you want to make sure you have a good grounding in this. Please feel free to leave a comment. It really helps me, and hope to see you again next time.